All right, hi everyone. Hello. Hi there. Hi. Hello. Hi. Hi. Hello. Hey. All right, let's get started. So today we're gonna talk about tree recursion. Hey. Hi. Hey. Hi. Today we're gonna talk about tree recursion. So first we're gonna talk about just a little bit of like review from yesterday, and kind of dive deeper into like how recursive calls work, because the order of how we evaluate recursive calls is extremely important when we talk about tree recursion. So tree recursion is this new idea we're going to be learning today, where you can make more than one recursive call in the same program. After that, we'll talk about two applications of tree recursion, and we'll finally see how recursion differs from iteration. Because in last lecture, we saw that you could do like factorial with a loop too, but we'll see in this lecture that recursion is actually useful for some things. So this is going to be like the application type of lecture. All right, so let's jump right in. Announcements. So first up is Hog is still due Friday, and if you submit by Thursday, you get 1 extra credit point. There are no office hours on Friday, so make sure you schedule accordingly. And some tips for final strategy. The main idea, I think, is to try to think like a human player. I've seen like a lot of students in office hours asking for help on this. One tip is to try to force favorable swaps by taking advantage of the rules. Like swap strategy, for example, we came up with one way to use the free bacon points, for instance, to try to force a swap, but try to look in the rule set to try to figure out how else can I control the number of points I get to force a swap. Avoid unfavorable swaps if possible. So whenever you can control the number of points. So basically on that same idea, if you can find a rule in the game that allows you to control the number of points you get on a turn, that's a pretty good deal. And lastly, if we're close to the goal, think about how we can play conservatively. So if you're close to the goal, maybe you want to adjust your strategy. Like if your score is this much, or if you're leading by a lot, try to figure out like maybe I can adjust my parameters to the number of rolls I want to do. And of course, you're always free to discuss ideas with others, so long as you make sure that you write your own code. So the final rule is that you write your own code, but I really want to encourage you to discuss, especially this last problem, final strategy, because it's like the perfect problem to discuss with others, right? It's like all about these ideas that you have about how you want to improve your strategy. So definitely discuss with others, but make sure you write your own code in the end. All right, so homework 2 is going to be extended to Saturday to give you a little more time to focus on Hog. So again, don't procrastinate, because homework 3, no time for applause. Homework 3 has just been released. That's going to be due next Wednesday. Homework 3 is probably, I think, one of the most instructive homeworks in the entire semester, because this is where we really teach you kind of deeply about recursion and whatnot. Yeah, question?
I thought you said we did a whole week to focus on homework 3.
Well, you do.
No, we don't.
It's due Wednesday.
Friday.
All right. If you're a hater, you can come talk to me later. We can figure something out. All right. Remember to ask Stan for hints tomorrow. So this will kind of make up for that a little bit. And quiz 2 grades will be coming soon. So as long as you completed the quiz, you're all good. But I want to give you like a report card to figure out like where you are with that environment diagram problem. I also made like a little video earlier, so you can watch that as well. All right, cool. Now on to actual content. So this week, we're talking about functions. And the goals for this week were to understand functional abstraction, which is to treat a function as a black box, to say, I don't really care about how this function is implemented, but rather how it works. Yeah, 2 quick questions. Yes? I don't have any hints. Well, I kind of gave one yesterday with ping pong. So if you remember the hint from ping pong, that will be useful. Okay, I don't know. It is on. I have the speech volume at maximum, so I don't know. Do you just want me to shout? I can like talk a little bit louder. Is that okay? Yeah. Okay, cool. Got it. Any other questions before we move on? All right, cool. So we talked about functional abstraction, where we treat a function as a black box. We talk about its behavior rather than how it performs some computation. And so we studied this idea through higher order functions, which we talked about on Monday, recursion, which we talked about yesterday and now today. And tomorrow, Stan will talk a little bit about methods of abstraction that go beyond functions. So today's lecture is really about why we care about recursion. Because we saw yesterday that we could do factorial, but we already knew how to do factorial with iteration. So today we'll present to you some problems that are hard to do with iteration, but are a lot easier to tackle with recursion. All right, so as a quick review, I wanted to bring up a problem from last lecture. So I showed you this countup example. So let's run through this really quickly. So I defined a countup function, and what this function does is it'll print up to the number 5. So it'll print 1 on a new line, 2 on a new line, 3 on a new line, 4, and then 5. So let's see how this program does it. So I've defined like a bunch of if cases. Because I know if I just want countup of 1, I can just go ahead and print 1. If I wanted to countup of 2, I can just go ahead and literally like write the code in to do exactly print 1, print 2. So this is like one approach that's called recursion by enumeration, and it allows you just to say, I don't really know how recursion works, but if I just figure out the pattern, maybe I can make some progress towards solving this hard problem. Yeah. So since I'm n equals 5, I'm not 1, not 2, not 3, not 4, but I am the else case. So in the else case, I made a recursive call with countup of 4. So now I've made a new frame. So this is kind of an important detail, especially for today. I made a new frame with different arguments, right? And this idea of holding different arguments is how I keep track of different bits of information. This is how I know I'm in a different recursive call. Okay. So then now I'm going to the n equals 4 case, and the n equals 4 case tells me to call countup of n equals 3, and then later on print 4. So countup of 3, we use the 3 case, and the 3 case just has 3 instructions. Print 1, print 2, print 3, and then return none. And so when we return none, this is the critical detail. When we return none, we go back to the person who called us, right? We go back to countup of 4. So we go back to countup of 4, and we pick up right where we left off. We did all that work of printing 1, 2, and 3 to compute countup of 3. So now that we finished that line, we can then go to print 4. So if I go print 4, what I'll do is I'll see 4, and now countup of 4 is done. So now to remember who called countup of 4. Well, if we go back to frame 1 now, we should go back to this line, countup of n minus 1. And so we just finished computing countup of 4. So we go back and finish the next line, which is print 5. And so that gives us our result, 1, 2, 3, 4, 5. All right. So we're going to look at the structure of the recursive function. So remember from last lecture, we talked about the 3 parts of a recursive function that are absolutely essential, and they're just as essential today. So a recursive function has 1 or more base cases. So in the example that I brought up with the concert, we said that if you're at the front of the line, you already know that you're the first person in the concert. And then you have 1 or more ways of reducing the problem using solving some kind of smaller problem using a recursive call. So this is where I ask the person in front of me, what number in line are you? And the third part is one or more ways of solving the original problem using the answer from the smaller problem. So when the person in front of me figures it out, when they answer this question, what number in line are you? So essentially, when that countup returns back to me, I add 1 to that answer, or in the example of countup, I print n. So I just do some additional work to essentially do my part, right? All right, so the order of recursive calls, I'm going to bring up a new example. It's kind of similar to countup, but it's got a neat new twist. So the example I'm going to use is this function called cascade. And what cascade does is it prints a very elegant cascade of numbers. And we'll just kind of see it in action, just to like show it to you, just to demonstrate how it looks and how it works. So I define a function cascade that takes in some number n. And what it'll do is it'll do some kind of printing of that number, kind of similar to what we saw with countup. Except instead of doing n minus 1, we do this n floor divide by 10 operation. which in effect says if I floor divide 1, 2, 3 by 10, I'll get 12. If I floor divide 12 by 10, I'll get 1. So if we kind of jump through and see what happens, I define the cascade function. I call cascade with 1, 2, 3 as the arguments. And so I look for the correct case, n is not less than 10. So what I'll do is use the else case, and I'll print 1, 2, 3. That's where you get that 1, 2, 3. Then I'll make a recursive call with the argument n, which is 123, floor divided by 10 to give me 12. So I should be calling cascade of 12 and opening a new frame here. Cascade of 12 with a new frame, n is not less than 10. So I'll use the else case. I print 12, then I call cascade of 1. And cascade of 1 finally uses this base case and prints 1. So we've counted like down from 1, 2, 3, 1, 2, 1. So now that we've finally returned, we can go back to the person who called us. And that was countup of 12. So we pick up where we last left off on countup of 12, and then we're going to print 12. Now that we return from this function, we can pick up where we last left off from 1, 2, 3, and we can print 1, 2, 3. And so this is what the cascade function does. It prints a very elegant cascade of numbers, starting from the full number, lopping off digits one by one. So you're like shrinking like a triangle, and then growing back like a triangle. So we saw how cascade worked here. I'm going to break that down a little bit more because it's an important example. So the key point I want to bring up here is how the different recursive calls kind of interact with each other. So we know the output at this stage looks something like this. So at this stage of the program, we've called 1, 2, 3, called 1, 2, called 1, and we got these 3 lines from that. We finished from 1, went back to 12, and just printed 12. So each cascade frame is from a different call to cascade. And we know that because we give it different arguments, and we're invoking a new call expression. We're making a new function call. Until the return value appears, that call has not completed. So essentially, the thing I want you to notice is that we went all the way down to cascade of 1. So we went down this like really long chain of calls, did all this work, and didn't come back until we finished one of those recursive calls, right? So any statement can appear before or after a recursive call. So there's like no rules on saying that, kind of like fact that we saw, fact went at the end of the expression. There's no rules on that. You could have this recursive call in the middle of your program, at the beginning, at the end. You evaluate that expression just like any other call expression. So no special rule handling by Python. All right, so as an example, if we take a look at that, you can put print n before the recursive call, or print n after the recursive call, or both of them. And we see that this frame here corresponds to the base case, and that's responsible for this line. And we'll see here that the frame for 12 does print of 12 and print of 12. So you can think of it as like a composition where I do print of 12, I call cascade of 1, which just prints 1, and then I do print 12. So one way of viewing this recursive program is to kind of like lay it out flat. Because I know cascade of 1, all it really does is just print 1. So cascade of 12, you can think of it as saying print 12, print 1, print 12. And so that's responsible for these 3 lines. And so I wanted to show you just another technique that's useful for us, because you might have noticed that there's some redundant code. So this is our definition for cascade. It starts with a base case, and then it has an else case that demonstrates that I do this recursive, right? So I'm going to show you a quick demo of how we might try to simplify this code, because it looks like there's repeated code. All right. So what I have here is the same cascade code. I also have a doc test. So let's go ahead and check to see if it works. Python 3-m doc test demo.py. So it looks like the cascade function works. It prints 1, 2, 3, 1, 2, 1, 1, 2, 1, 2, 3. But we do notice that there is some repeated code here, right? Print n and print n appear in both of these cases. So no matter what, this program will do this, will print n. what we might notice is that we could simplify this code by giving both cases the print n, right? And if we instead make it like an implicit base case, we could say if n is greater than or equal to 10, then I can do more work and call the cascade function. So logically, these two programs should work the same, right? Because in the base case, I'll print n, and I'll skip that if clause, right? In the recursive case, I'll print n, and then go in the recursive if clause. So if we test our program out, we should see that this program still does in fact work. And just as a sanity check, it's useful to pull it up in the interpreter and type cascade 1, 2, 3. And we should get exactly the same code. So we have two logically equivalent definitions. Of cascade. And so the question is, which one should you use if you were to write this on program or write this in your homework or in industry? So as a general rule of thumb, we like brevity. We like programs that are short. So this is like speaking to composition if you're thinking about Hog, for example. If two implementations are equally clear, the shorter is usually better. But in this case, I think the longer implementation is a little clearer because it says explicitly this is the base case and this is the recursive case. So to someone who's reading your code, or maybe even yourself, like 6 months down the line, it's useful to have like these explicit cases that says, this is what I'm gonna do in the base case, and this is what I'm gonna do in the recursive case. Because it might not necessarily be clear to someone who's reading your code how exactly this program works. It looks like I'm just always printing n, and then under some weird conditions, I sometimes make a recursive call. So that vagueness in terms of like where the base case ends and where the recursive case begins makes this implementation a little bit more difficult to understand. So when learning to write recursive function, it helps to try to put the base cases first. And we'll see on the way we structure, like for example, the skeleton code that we give you on assignments or on the exam, we like to put the base cases first. And so I'm going to give you a quick example of something for you to try out on your own. So this is going to be a function that's called inverse cascade. And what it'll do is when I call inverse cascade of 1, 2, 3, 4, it'll do this. So instead of doing a triangle from the 1, 2, 3, 1, 2, 1, instead of a triangle that shrinks, we have a triangle that grows first, and then a triangle that shrinks. But the main challenge for this program, though, is I want you to write it using a very high level of abstraction. We're going to define 3 functions. Well, 2 of them, I suppose. We're going to define grow, which will be responsible for printing these 3 lines. And then we're going to define a function shrink, print that can do, shrink that can print these 3 lines. And then print is already given to us. And we'll have one helper function f then g that will, under the condition n is true, or when n is a true value, we will call f of n first, and then g of n. So your job is to write a definition for grow and for shrink using this skeleton. So I give you a lambda function that takes in one argument n and returns a call to f then g, and you have to figure out what arguments to put here. Question mark, question mark. So spend a minute or 2 thinking on your own. Then I'll give you a couple hints, because I remember when I did this problem, I could not even get started. So spend a moment, think about it on your own. Then I'll give you a couple hints to try to give you a head start on this. And then after that, I'll give you a chance to talk. So think, hints, then talk. It helps to have paper out, by the way. All right, ready for a hint? You want a hint? No? Don't want a hint? You want a hint? Yes? No? Yes? Hint? I see only 3 people participated. Okay, let's try that again. Do you want a hint? Yes, okay. So the first hint is, which one should be responsible for printing? So let's think about grow first. Which of these should be responsible for printing? And which one should be the recursive call? Because we know there's some relationship between what we just saw with Cascade and this program here. And since we know the topic is order of recursive calls, we have to figure out, our job is to figure out which one of F and G should be the one that prints and which one should be the recursive call. That's one part of it. The second hint is for N, how should we define when to stop? What's our stopping condition? So we have to define a function, f then g, or my bad, we have to make a function call to f then g, and we have to figure out what are the 3 arguments. Should f be print? Should g be the recursive call? Should n be, I have no idea. So spend another minute or so thinking about that, and then I'll give you a chance to talk about it with the people around you. Because we know we're going to have to use print somewhere, we know we're going to have to use a recursive call somewhere. I just see a lot of stares right now. It is pretty hard. I definitely could not have answered this. I definitely did not answer this when I took this course. I was pretty stumped. So don't feel bad. All right, so now that you've had a chance to think about it on your own, go ahead and turn to the person next to you and talk about what your ideas are so far. It's fine if it's not totally fully formed, because that's kind of the point of talking.
I don't know what it is. Sorry.
All right, let's come back together. Enough talking. All right, let's go. Let's see the answer. Let's grow. What is that? Okay, let's think about it this way. I was just talking to Grace and Aiden in the back, and they were really cool people. So let me just share with you what I kind of came up with, or what we all came up with. So here, what we're going to do is we're going to call f then g with grow, print, and n divided by 10. So since we know this is the answer, let's suppose that this wasn't the case. Let's suppose we put f as print and g as grow. And let's just think about what happens then. So if f is print and g is grow and n is just something that evaluates to a true value, what we'll do when we call grow in inverse cascade is we will call f then g with print grow in something that's true. And so we'll go in here, we'll say n is something that's true, so we'll run this case. And since we know f is print, what will be printed out? What's n at this time? Sorry, can you repeat it? Shout it out. 1, 2, 3, 4, really meekly. Because we're at the very beginning. We haven't changed anything with the number 1, 2, 3, 4, right? When we call inverse cascade with 1, 2, 3, 4, we go here, n is 1, 2, 3, 4. We're going to call grow with 1, 2, 3, 4. And grow says we're going to call f then g with grow, print, and n divided by 10. So in this case, n will be 1, 2, 3. So we'll have 1, 2, 3 passed in here. We'll call f, which is print, and we'll print 1, 2, 3 as our first line. So this is kind of going in reverse then. If we simulate what happens when we put print first, we'll get it in reverse. We'll have 1, 2, 3, then 1, 2, then 1. So I wanted to show you that in an environment diagram because that will help as well. So we close this one. Here is a simplified version of the problem. So if I just call inverse cascade with 12, and I pass in the exact code that we just wrote, what we'll get is, I'll call inverse cascade, and inverse cascade, oh my bad, we'll define inverse cascade, define grow, define f then g. So when we call inverse cascade, we'll pass in n being 12. We'll call our grow function with 12. And what grow says is n is now 12. And what I'll do is I'll return the value I get from evaluating f then g with grow, print, and n divided by 10. So calling f then g, I go in the body for f then g. Oops. I go in the body for f then g. I check if n is true. So n is a true value. 1 is a true value. So what I'll do is I'll call f. In the correct case, I'll call f, which will go to 1. And now I'm going to call f then g with 1 divided by 10, which will give us 0. So now when I look at this frame, n is 0, which is a false value. So in the correct code, what we'll get is nothing happening for the 0 case. Then when we return back to the F call, we'll finish the F call because we did nothing in the F call. And then G now is responsible for printing. And so we get printing 1 for growing and then printing 12 from the print function. How do you feel about that? Yeah, I feel you. Let's do that again. Do you want to see the correct version or the incorrect version? Because I showed you the correct version. I think I might have confused all of us because I talked about the incorrect and then now I showed you the correct version. So let's redo that, okay? Let's see, do you want to see the correct or incorrect version first? Correct? Okay, so this will be this one again. Okay. Let's do the correct version. So we define the 3 functions. So far, so good? Call inverse cascade. Now we're going to call grow with the argument 12. And what grow says is it's a function that takes in one argument n, and that n is going to be 12. Right? And the body of this lambda tells us I am going to return a call to f then g with the arguments grow, print, and n divided by 10. So to evaluate this, I know what f then g is, I know what grow is, I know what print is, and n divided by 10 is going to be 12 divided by 10, or 1. So what I'm going to do is I'm going to call f then g with grow, print, and 1. So I should see a new frame for f then g with f pointing to the lambda function that is grow, right? So it's a lambda that takes in n. That's our grow function. G is going to be the print function. So it's the built-in print function. And n is going to be the one that we passed in. With me so far? Yes, no, yes, good. Okay. So we're in f then g right now. And what we say is, if n is a true value, and in this case n is 1, because in our current environment, we're looking up here, our current environment is f3 then global, so we say n is 1, so it's true value. What we'll do is we'll call the f function. So in this correct definition, the f function is going to be grow. So we'll recurse down. This is like the recursion step that goes down. If you think about it in terms of cascade, it's like we're going all the way down to the base case with grow. And then after we finish the base case for grow, we're coming back up. We're getting our answers back. So we're going back down. We're going down for now. So we're going into grow. And now when I call this function with n equals 1, what I'll do is I'll call f then g with the argument grow, print, and now n being 0. So we know if we skip ahead a little bit, if I call f then g with n being 0, that's going to be a false value. So when I look in f then g's body, oops, scroll over, this should evaluate, this Boolean expression here should become false. And so I'll skip the if, and I'll return from f then g because I'm done. Essentially, this is where our base case is. When n was false, when n is 0, it's false, right? It's a false value. So this becomes our base case because we don't run the inside of this if. So now that we've reached that base case for inverse cascade, we're going to go back to the person who called us. We're going to go back to grow because that was where I was called from. And this grow is going to go back to f because that was where the lambda was called from. Do the steps so far make sense? Yes, no? And I think 2 people responded. Let's do that again. Yes, good. Medium, not really. Yeah, I think this is a very hard problem, so it's just has to stare a little bit more. We'll see more of this as well, but if we look at, we just finished f, which was going down. We hit that base case, right? So kind of similar to what we did with cascade or count up, for example. We went all the way to the base case with count up, and then once we finish that base case, we come all the way back to where we were called and do the next thing, the next line in the code, which asks us to do g of n, and g of n is going to be the printing. So I'm going to print 1. So now that that's done, I'll return none and go back to the call to grow because that was from this one. So I think the main challenge for this is because we have like a lot of intertwining calls to grow, it's kind of hard to see what's going on. But this call to grow, the reason why we're back here is because we just finished f then g. We just finished that job of printing 1. We just finished the main grow call. So we should return back there and compute the next thing, which is the print, 12. So it's okay if you don't understand that for now. Try your best to follow along. Watch it again later. Think about it some more. Questions about that? You want to go over something maybe really quickly? Yes.
Oh, but that doesn't give you a 1, right?
Sorry, at the end?
Yeah.
Right, because it would be too long if I added shrink.
Oh, but shrink.
Yeah.
Okay.
Yeah, so I took out shrink here because it would be like too many steps. I think it's already hard enough understanding this. Any other quick questions? I think we're all just really confused right now. Okay, so we'll have more practice with this in the future. Don't worry about it. So if we look at shrink, we can define shrink similarly. If we know the incorrect, or suppose if we know the correct version of grow wants to recurse down to the base case, so we can reach the 1. We want to reach the number 1 because we want to print that number 1 first, right? We recurse down to reach the number 1 because we want to print 1 first. If we want to print 1, 2, 3 first, we should have print come first and then recurse down, right? So whereas what we did with grow was recurse down and then print back up, what we want to do with shrink is print on the way down, and then as the recursive calls close, as you return back to the caller, we should be able to see, we should be able to do nothing, basically. So we'll see here that we print on the way down, we print on F, we print as we're going down. And then the shrink call is responsible for making those recursive calls, and then as the frames close, as we return back up, there's nothing else to be done. Questions about this? So I really want to focus on the way that the recursive calls return. Yeah, so as you're going down, there's like a procedure that happens kind of invisibly. You can think of it as like, before we get to printing 1, we do a lot of work with grow. We start with 1, 2, 3, 4, right? We call 1, 2, 3. We still don't print anything. We call 1, 2. We don't print anything. We call 1. And only when we get to 1 do we start going back up. 1 or 0, and then we start going back up. And then when we go back up, that's when we start printing. We print 1. We print 1, 2 on the way back up. We print 1, 2, 3. We print 1, 2, 3, 4. And the way shrink works is kind of opposite, whereas we print on the way down. I first print, and then I make a recursive call to 1, 2, 3. And I repeat that process. I print, then I recurse. I print, then I recurse. And on the way back up, I just do nothing, because I don't need to print any of the smaller numbers. That's kind of the intuition. I think it's fine not to totally understand the environment diagram, but at least try to get that part of it. That I do something on the way down, and I can do something on the way back up. Does it make sense what I mean when I say on the way down and the back up? When I'm making the recursive calls and the recursive calls return. Questions? Yeah?
I think the one reason that I'm confused is the terminology of grow. Because it seems like grow implies you start from a small number and then get bigger. And then that kind of messes with the recursive order.
Right. So what's your name?
Martin?
Yeah, Martin's, I've asked your name like 3 or 4 times. So Martin's question was, it's kind of tricky trying to figure out how grow works because its name kind of doesn't really match up with how the function works, right? Because really, we don't grow, we shrink. We shrink first, and then we start printing on the way back up to get this growing effect. So it's a little weird because that's how recursion works. In order to reach that 1, if you want to do print 1 first, you have to go all the way down. Yeah, so it's kind of like a side effect of how we think about functional abstraction. We call it grow because that's what it looks like it does, even though the implementation is really tricky. Okay, cool, enough of that. Fibonacci, gonna move on. This is a fun topic. just to contrast with inverse cascade. So let's talk about Fibonacci's rabbits. So there was a man called Fibonacci, and he was interested in this problem. He was interested in the problem of how do rabbits reproduce. Okay, yeah, so if we look at this picture, we start with one pair of rabbits, and they're just living but rabbits like to reproduce. So they mate, but it takes a while for them to produce baby rabbits, like bunnies, I guess. It takes a while to produce bunnies, right? So it takes a little bit more time to produce bunnies, right? So this is the bunnies, because they're new, and these are the parents. And they mate again, and they mate again, and they mate again. And for each time they mate, they make a new pair of bunnies, and those new pairs of bunnies will try to mate as well. So if you think about it this way, we could say this is like a sequence that looks like at time step 1, I have one pair of bunnies. At time step 2, I have still only one pair of bunnies, or one pair of rabbits, but they're ready to reproduce. At time step 3, I now have 2 pairs of rabbits. One that is trying to reproduce again, and one that is just a new pair of bunnies, so they can't reproduce just yet. At time step 4, this really hard-working pair of bunnies is still trying to reproduce. And they've already made a new pair of bunnies, right? And this new pair, like from time step 3, can now try to reproduce. And we keep on repeating this process at time step 5, I have 5 bunnies. At time step 6, I have 8. And so the structure I want to point out is that there is something that is recursive about this structure. Because if we look at here, to compute the number of bunnies at time step 3, I take the bunnies I had at time step 2. And then I add the number of bunnies I got from time step 1. This is the really weird part. I add the number of bunnies from time step 1. Why? Because this is a new pair of bunnies, right? If I'm just mating, I make a new pair of bunnies, right? So that's responsible for that. So now if I have 2 pairs of bunnies, one that can mate and one that needs a little more time, they'll still be here, right? But then now on the next time step, one of those pairs will be able to do that. We'll do that mating. And so we can kind of see that each one kind of feeds into the next. So we have, to compute time step 4, for example, we use the results from time step 3 and from time step 2, and we add them together. And so that gives us some intuition for the Fibonacci sequence, which actually I think originated from India. So even though we'll put Fibonacci's face right here. Here is bunnies, really cute. And this is the sequence again. We saw that at time step 0, we don't have any bunnies to begin with, but at time step 1, we have 1. At time step 2, we still only have 1. And at time step 3, 4, 5, and so forth. So the thing is with this sequence is that it starts off really slow. We saw that we had 1, then that 1 had to mate, and then we had 2, and then we had 3, and then we had 5, then 8. But we'll notice that the sequence grows very, very quickly. In fact, really quickly. When you get to 35, you have 9 million bunnies, and you're like, why? And so the way this computation works is, just to recap, I take the last 2 items in the sequence, the last 2 numbers in the sequence, and I add them together to get my next number. So this is actually a pretty hard problem to solve using, this can be a hard problem to solve using iteration, because you're not necessarily sure, like, I need this many variables or this many things to keep track of. One thing that's nice about recursion is that we have a more elegant solution. So we call this solution a tree-shaped process. It's a tree recursive program. So tree-shaped processes arise whenever executing the body of a recursive function makes more than one recursive call. So let's flip back a little bit. Remember here, to compute at time step 5, I need to use the results from fib of 4 and from fib of 3. So I need to make 2 recursive calls to compute fib 4 and fib of 3. So if we look at how we define fib here, we'll say I can define the fib sequence taking in one number n, and let's consider the base cases. If n is 0, let's return 0. Otherwise, if n is 1, return 1. So these are the 2 facts that we had from this sequence right here. If n is 0, return 0. If n is 1, return 1. And in the recursive case, it's just a really simple line of code. Else return fib of n minus 2 plus fib of n minus 1. And that's where you get the 2 previous results, right? For example, to compute fib of 5, I use the results from fib of 4 and fib of 3. So I'm going to show you a quick demo of how that works. So in the interpreter, Get out of here. Here we go. All right, so fib, let's look at how fib of 5 works. So I mentioned that if we call fib of 5, we'll go in the fib function. We're not 0, not 1. We're going to use the else case. And so here's the important detail I want you to remember. This is like why we talked about order of recursive calls. Because if we look at this recursive case, we're making 2 calls to fib. So the question is, what is the order in which we evaluate these calls? And we know that because this is just a call expression, this is a plus sign, so it means we're adding 2 numbers, right? Adding 2 items, not necessarily numbers. We're adding 2 items. And so we evaluate the left operand, which is going to be a call expression. So what we'll do is we'll evaluate fib of 3 first. So fib of 3. And we'll do the work for fib of 3. It's not either base case. So we'll go to the recursive case again. And we repeat this process of evaluating the recursive case. We say, we know this operator is the add function. And we will add this operand, which we don't know yet. So we have to evaluate it. Fib of 1. And so fib of 1 is a base case. So we will return 1. And we'll return 1 back here. It's like we're saying for the fib of 3 case, we know the answer to fib of 1 is now 1. And so we get 1, but we remember it. We don't do anything with it in the environment diagram. We just remember it. It might be helpful when you're doing this on paper to actually write down what the value is on an intermediary step. So we're just holding it in our heads that this is 1, and then we just go ahead and jump to compute fib of 3 minus 1 or 2. That's what's going on here. We evaluated this one to 1, and now we're evaluating the second operator. So to evaluate the second operator, we call fib of 2. It's neither base case. So we call the same procedure. It's the add function, fib of 0, and then fib of 1. So we figure out fib of 0 returns 0. Fib of 1 returns 1. And now we have the ability to produce an answer to fib of 2. And the reason why we get 1 is because when we called fib of 2 minus 2, fib of 0, when we called fib of 0, we got 0. When we called fib of 1, we got 1. So 0 plus 1 is 1. And that's why we get this answer to fib of 2. And so guess the next step. Where do we go back? 5, 4, 3, 2, 1. Okay. So we did all this work of computing fib of 2. Why? We have to remember where we came from. What was I going down this rabbit hole for? Rabbit hole. Oh. I was calling fib of 3, right? I wanted to know the answer for fib of 3. Let's get that straight. I wanted to know the answer for fib of 3. So the answer to fib of 3, I had to call fib of 3 minus 2, fib of 1, which we remembered earlier was 1, right? And then we did the other part, which was computing fib of 2, which we now know is the answer is 1. So now that we have both parts of that addition operation, we can now say 1 plus 1 is 2 for computing fib of 3. And now to remember, why did we compute fib of 3? Because fib of 5 called us. Fib of 5 said, I need fib of 5 minus 2 or fib of 3. And now we know fib of 3 is 2. And so we keep on doing this. And now we have to do fib of 4. So it gets kind of out of hand with all this jumping around with the trees and stuff and whatnot. Are there any questions about this? Do you want me to replay something? Yeah, go for it.
How come when you put the 5 in the fib minus 1, you not get fib 4?
Oh, good question. Can you repeat your name? Sorry? Ethan? Yeah, so Ethan's question was, why do we not get a fib of 4 frame? And I think that's the next step, actually. So it should be right here, fib of 4. Yeah, so we did, when we were doing the original call of fib of 5, remember that our goal is to compute fib of 3, which we did all these F2, F3, F4, F5, F6. So we opened 4 frames to compute fib of 3, and then just now do we start computing fib of 4 using this new frame. So there's a lot that's going on here. And so this is kind of hard to visualize in an environment diagram because it goes in like a lot of detail. So what I'll do is I'll show you a visual here instead. So we start with the call of fib of 5, right? And we know that fib of 5 will call fib of 3 and fib of 4, fib of 3 and fib of 4. So we have fib of 3. And what fib of 3 will do is it'll do all of this. These are like the frames F2, F3, F4, F5, F6. And each of them has to compute some kind of answer from a base case. Notice that all of these final values here, like the 1, the 0, the 1, these are all from the base cases. We take all these results from the base cases and we compute bigger answers like fib of 2 using fib of 0 plus fib of 1. 0 plus 1 is 1. So that's where we got that 1 from, fib of 2. And to get the answer to fib of 3, we took 1 plus 1 from fib of 2, added those together to get 2, and that's the answer to fib of 3. And so on the right side, well, my bad. So the procedure or the evaluation order basically looks like this. I start from fib of 5, I call fib of 3, call fib of 1, finally compute fib of 1 as a base case, and then keep on going. Call fib of 0, fib of 1, fib of 2. And then only then, now that I've computed all the way up to fib of 3, I can start looking at the fib of 4 call. So that's why fib of 4, that n equals 4 frame, took so long to get to. I had to wait until frame 7, F7, right, to get to fib of 4. So only then do I call fib of 4. And fib of 4 is an even bigger tree. So we have so much work to do here. We have to visit fib of 4, which has to call fib of 2, which has to call fib of 1, which has to call fib of 0. And then fib of 2 computes 1 plus 0 is 1. And then fib of 3, we have to call fib of 1, which computes 1. And the other part of fib of 3 is fib of 2. So that has to call fib of 0 and fib of 1. And it's just a huge mess until we compute all the way back up by adding all of these base case results. Yeah, Martin, go for it. Got your name this time. Right, yeah, I think that's a mistake on my part. So technically the order for execution for these two should be flipped. So I think I just copied them incorrectly somehow. How? There's like 2 of them are right, but like 1 of them's wrong. Thanks for pointing that out, Martin. So it should be fib of 0 on this side and fib of 1 on this side. Bizarre. Mm-hmm.
So what would be the way to write this so that it occurs more quickly?
Yeah, great question. What's your name?
Tristan.
Tristan, what's a way to write this so that it occurs more efficiently? So in this class, we're actually not super concerned with efficiency. We're more concerned with the correctness. But we will teach you, I think kind of shortly, how to write a more efficient version of this. And it unfortunately kind of goes back to iteration. So I kind of lied and said that this was useful, but not for this problem yet. Later, wait, you'll see it. All right, so I wanted to show you what happens when things go wrong as well, because I think this is a useful point of discussion too. So we saw that fib of n, we could define it like this. I could define it with just n equals 0, return 0, and I just don't include any other base cases. So remember in the correct fib, we said we had n equals 0 as a case, as well as n equals 1 as a case. And we just jump straight into the recursive case. So if we run this code instead, we call fib of 3, what do you think will happen? Spend like 30 seconds, 15, 30 seconds thinking on your own. Hold that answer in your head and we'll go over it. Right, call fib of 3, where do I go? All right, so hold that answer in your head. Let's see it right now. So 3, 2, 1, ta-da! Recursion depth exceeded. Why does that occur? Why does that occur? Let's talk about this. Hi. All right, let's calm down a little bit. So the missing base case here means that there's no stopping point for this recursion. So if we think about it this way, I'm calling fib of 3, and I know fib of 3 will call fib of 1 in the fib of n minus 2 case. It'll call fib of 1, and fib of 1 will call fib of n minus 1. Oops, n minus 2. So it'll call negative 1. And what this call will do is, because I don't see a base case for either fib of 1 or for fib of negative 1, we'll keep on using the recursive case. And so forth. So I'll call fib of negative 1, fib of negative 3, fib of negative 5, forever and ever and ever until Python gives up and tells me, hey, I think there's something wrong, runtime error. So to visualize this in the picture, so as a tip, you should also always check for missing base case if you see this error. So if you see this error, check for missing base case. As a visual, if we look at how the broken fib executes, let's say we're evaluating fib of 5. We call fib of 3, which calls fib of 1. And here's where it goes wrong. When we call fib of 1, it's no longer a base case. So because we don't have a case for fib of 1, what it'll do is it'll use the recurse case. It will call fib of -1. And fib of -1 will call -3, and so forth. And so we will never end up executing any of the rest of that tree because we're so preoccupied with following this line of thought. Because we know that we can't go back until someone returns. And none of these calls are going to let up. They're not going to return until someone says, hey, I'm a base case. So these calls won't return until we hit a base case. So the problem is we keep on going all the way down there and we forget about the rest of the tree. Yeah, question?
That function, wouldn't that like be the right side and -2 is the second branch?
Yeah, I think I flipped around the order of those. So this is like another mistake on my behalf. So I'll fix that in the slides later. Is that okay? Yeah, thank you. What was your name again?
Will.
Yeah, Will, thank you for pointing that out. Okay, yeah.
And in the last page, there is a maximum recursive depth. So is that converter in the Python runtime or is something different? Because if I input a very, very large value in this function, will it be the same error or no?
Right, so what's your name?
Frank.
Yeah, Frank's question was, how does Python detect this, kind of? Yeah, so the way Python detects this is that it keeps track of like how many times I'm recursing on the same function. And it says like after like 1,000 times I give up. I just assume that your code has some problem. So even if your fib is correct, even if you have like a totally correct Fibonacci like this, if you give it a big enough input, Python will still say recursion depth exceeded. Because it just says you did over 1,000 calls, and I'm really scared right now. So yeah, it could be the case that you give it too large of an input as well. That is true. You can also change that setting in Python, but that's a discussion for later. All right, so moving on. Let's take a break. This next part's gonna be really fun. Yeah. Hi. I'm really tired.
Yeah, I have a question. So, what are the criteria for being graded for composition? So, our project is graded for correctness and composition.
Right.
What does it mean?
I think it's like, have you read the composition guide? We have like a little guide that says this is what we look for in composition. Actually, I think it might not be that easy to find. So I'll post it maybe on the website. Make it more easy to find. Yeah, I think it's hard to find the composition guide, so I'll make it more visible. Yeah, but I'd say don't worry about it because
This is just passing okay, right?
yeah. So if you pass all the tests on your side, you're good. Yeah.
But what I mean, if my code looks like kind of complicated for someone, is it the right composition?
Wait, sorry, is it correct or?
For example, something like that, or like I said, you see like the operator, net,
I think that's fine.
Is it fine?
As long as it's not too long. Because like, when it gets really long, it's hard to tell. I think that's still fine. Yeah.
So there's something specified. Is it like
Yeah, if it's really long, it can be hard to like tell like what's what. Maybe. Yeah.
okay?
I have a quick question. From in your slides, when you were explaining it, you kind of made it sound like when we go down the recursive tree, if we compute the Fibonacci of 1, we can use it, the result in the other trees. But that's not correct, is it?
It has to be recomputed each time, right? That's why we have that huge tree. Because like, you see fib of 0 and fib of 1 a
So
lot.
there's a new frame for every Fibonacci of 1, 2 that we need.
Right. Even if you've already computed on the left.
Yeah.
Python doesn't remember that.
Yeah,
But we do have tricks to kind of work around that and make it more efficient.
Yeah.
We saw there were like a lot of repeated areas. Yeah.
In the last example of recursion, we calculate many numbers for many times, which is repeated.
Yeah.
So how do we improve our method to avoid to do the same thing for many times?
So these are techniques that we'll learn in CS 170. It's an algorithms class, but in short, you can use this technique that's called memoization.
Right. Yeah.
Yeah, you can look it up online.
So can we use some data structures such as hash? So
Yeah, exactly.
yeah, but what is so it's just what you mean memorizing?
Yeah, just essentially you whenever you call before you call it,
Yeah.
you check to see if I've already computed
So
it.
we save the number. And
Yeah, we
next
just save
time
it.
We will check again.
Yeah, so before we call it, we just see if I've already saved it.
Yeah. So that's the best way to improve the efficiency of. Or do we have other ways?
That's just one approach because you still have to. The problem with that is you still have to call it, right? You have to call it, and then that call only then does it check. Well, you still have to make that call. Like even if it doesn't recurse, you still have to call it, right? So that it has that branch. You have to make a branch, but that's still expensive. So a better technique is to rewrite the algorithm, and we use an approach called dynamic programming for that. Yeah.
Got it. Thank you.
So I got a question.
Yeah.
I wrote some code that was basically if free bacon will make you instantly win, use it, and it lowered the percentage
yeah.
victory.
Huh.
Did you change? Is the goal score always 100, or does it change with the tester? Because if it changes, then that's why this is scoring lower. But if it doesn't change, then this should never score lower.
Never score lower? Oh, I'm not really sure.
Because I mean, it doesn't make sense, right? If you instantaneously win, that should not never score a lower percentage than normal victory.
I'm thinking. How does that work? The way our model works for computing the win rate is that it just figures out like there are like some states where you're more likely to be in. Like for example, the score 0, the combination of score 0 and 100, like if your score 0 and the opponent's 100, it's very unlikely. So we say that we won't give much weight to what you roll there. But for areas that are like kind of close, like a lot of games will be kind of close, right? So we say for a high probability you will be in this close a region. So like given that kind of weight, then like if I say that you're gonna do free bacon to get to this many points, I don't know. I feel like there might be something going on. Like maybe
Because that sounds like an error on the tester part. If that because this should never lower the score, but it is every single time. Maybe the way you're doing the weights. I don't know.
not really sure. Huh?
Is that
Think
totally?
about that.
Yeah, that's
I'm
what
not
they
really
screwed about. I don't know.
Yeah, what's up? Okay, hey, what's up?
Hi, I have a question. What's the difference between higher order function and recursion?
High order functions are just, you can think of them as just functions that either take in another function or like return another function. So they work with functions as their inputs or outputs. And recursion is a little different, I'd say. It has that same idea of treating, like the reason why we include higher order functions is because we want to treat it as a black box. We say, we don't care about how this function works, we just say it's a function that does this. And so when we teach recursion, it's not strictly a higher order function, I guess, because you don't always have to give it a function. It doesn't have to return a function, right? But it has this weird property of, you have to think of it like a black box. And you say, this is what the function does.
And also for the project, are we like? Is there any occasion we can apply a recursion function for like strategy?
For Hog?
Yeah.
Probably not.
Okay.
Yeah.
Thank you.
So
Yeah.
I can like visualize how you, or I can like understand how you would create like so I'm trying to create an array of like possible combinations for Hog.
Oh yeah, good idea.
Right. So I can do that in 2 dimensions or 2 dice rolls. But is there a way to create like a 10-dimensional array, if you will, in Python?
Wait, why do you need a 10 dimensional?
So like, because if I have 2 dice, then I get like 1 + 1, 1 + 2, 1 + 2, and like so forth, right? But then I'd need like a third one coming out to like add up all those combinations.
Okay.
Or how would I
Yeah.
achieve the same effect?
You can use like nested lists and then use like for loops to loop over them. Yeah.
Okay.
Yeah, just have nested lists. I guess the easiest way. All right. Hi. Back to the fun part. This will be pretty relevant for your homework. Hey, hi! Hello. Hi. All right. This will be pretty relevant for your homework as well. So definitely make sure to listen in. All right. So I mentioned earlier that tree recursion is useful, and we'll see why right here. So I'm going to introduce a new problem, and it's called counting partitions. And so in this problem, we define it as a really boring problem. The number of partitions of a positive integer n using parts up to size m is the number of ways in which n can be expressed as the sum of positive integer parts up to n in increasing order. What does all that mean? I have no idea. Let's give you an example. So I can call count partitions with two arguments, n and m. They're two numbers. And what that says is basically, how many different ways can I give out 6 pieces of chocolate if nobody can have more than 4 pieces? Counting partitions. Counting chocolate. Counting chocolate. All right. So the problem, just to repeat it again, how many different ways of giving out 6 pieces of chocolate, n pieces of chocolate, if nobody can have more than 4 pieces? Does this make sense? I'll give you an example of that on the next slide. So I'm counting chocolate now. If I call count partitions 6, 4, 2 possible combinations I could use are, I could give someone 2 pieces of chocolate and then give someone else 4 pieces of chocolate. I could give another possible combination is one person gets 1, one person gets 1, and the other really lucky person gets 4 pieces of chocolate. And so I can keep on listing out more and more combinations. Combinations with 3 pieces of chocolate. I can give one person 3, another person 3, one person 1, another person 2, another person 3, and so forth. And here are all the combinations. All the way down to just giving everyone 1 piece of chocolate. So if this is like the solution we want to get, we want to figure out how many of these combinations are there. That's the problem. We want to figure out how many combinations are there. We can kind of visualize the problem like this. I could say on one side, I can give this one person 2 and the other person 4, or I could give 2 people each 1 piece of chocolate. And you'll notice that the way we broke this problem up was by first subdividing it into this category. Of first finding someone to give 4 pieces of chocolate to, and then distributing the rest of those pieces of chocolate. So once I've distributed the 4 pieces of chocolate, I only have 2 pieces left. So then I need to figure out, how do I distribute 2 pieces? And wait a moment, isn't this recursive? I've just made a smaller recursive call, right? I said, I started out with a problem of size 6. I wanted to distribute 6 pieces of chocolate. But now I only need to distribute 2 pieces of chocolate over here if I give someone 4 pieces. Everyone good with the problem definition so far? Yeah? Thumbs up. Thumbs sideways. Arya.
If it was, if it was 6, 6, would it include 6 rows? Would it include a section where if someone 6 and others?
Yeah, so Arya's question was, if my maximum number of pieces for one person is 6, so instead of 4, if it was 6, if I can give one person 6 pieces, then I just go ahead and just, like, my first combination might be somebody gets 6 pieces. And that's it. Great question. That's how the problem works. Cool. Okay. So if we look at the rest of the combinations, it works out like that. Notice how this right side fans out. I first tried to find all the combinations of first giving out the 4, and then I left with the problem of size 2. I just need to hand out 2 more pieces after I give out one person 4. Then I tried to give out only 3 pieces of chocolate. And then my remaining problem is just figuring out, how do I give out 3 pieces of chocolate to however many people I have, and so forth. And so to really visualize that, we have a couple rules. This process is called recursive decomposition, when we try to find these smaller instances of the problem. So this takes some inspection. It's not always easy to find, and especially with the problems that we try to give you, they tend to be kind of hard to find, like where the patterns are. How do I come up with like a solution like this? And so the strategy for tree recursion in general is to explore 2 possibilities. we want to try using at least one 4, as on the right-hand side, the very right upper right-hand corner, or I could not use the 4. Right? And so I end up trying to solve 2 simpler problems. I showed you earlier that I solved one problem by saying, if I use the 4, then I should just solve 2 more. When we think about this recursively, I can rephrase the rest of this, like the blocks of 3s, the blocks of 2s, the blocks of 1s. I can rephrase that problem by saying, try to find the number of ways I can distribute 6 pieces of chocolate if I only have, if nobody can have more than 3, right? So instead of saying 6, 4 as in the whole problem, this bottom half kind of says 6, 3, right? Because this bottom half, the bottom half, this green area, is 6, 3. The number of ways of distributing 6 pieces of chocolate using partitions of size up to 3. So nobody can have more than 3 pieces. And if we look at that, it's exactly that. The problem 2, 4, which is phrased as, if I have 2 pieces of chocolate and I can give out up to 4 pieces per person, well, I only have 2 pieces, so I'm limited. So I can only have 2, or I can give 2 people 1 piece each. And then the 6, 3 problem becomes this entire space, which I can then further recurse on. I can then say, this is a subproblem that I can solve using this, and then this becomes another subproblem, and so forth. So we can define this program as follows. Or does anyone want me to review this? Do you feel good about this? Questions? We want to see how this ties into code. And so now we have some intuition for how we want to approach this problem. We know that we have essentially 2 cases to consider. What happens when I already give you 4 pieces of chocolate? In which case, I just have to subtract something, right? I need to somehow take away that 4 pieces of chocolate from my stock. Because if I've used up that 4 pieces, now I have 6 minus 4, or 2 pieces left. And so, if we look at the recursive case first, so notice this is something different about this problem. Sometimes with tree recursion, it helps to explore the recursive case first, if it's more natural, if it's more intuitive for you. We'll see in this problem that the base cases aren't very obvious. So we can write, like I just phrased, we can say count partitions of 2, 4 is essentially what happens when I use M, when I use 4 pieces of chocolate, when I give someone 4 pieces of chocolate. So this call corresponds with M, when I give someone 4 pieces of chocolate. And this call, 6, 3, corresponds to what happens if I don't want to try to give anyone 4 pieces. What if I say nobody can have more than 3 pieces now? And that'll find the lower half of combinations. And finally, I can return the sum of those number of combinations to get my total number of combinations. And so just to really link it up for you, the count partitions of with M requires taking from my stock, because someone is using that 4 pieces of chocolate. And the partition for 6, 3 says, keep my stock the same, because I'm not going to try to give anyone chocolate on this turn. Instead, I'm going to say, let's limit the number of pieces of chocolate you can try to up to 3 pieces. And so now the question is, how do we write our base cases? So we know we need some way of we know that these problems are going to reduce towards 0, right? I start with some big number n, some big number m, and they're eventually going to be subtracted down. So we need to figure out some way of handling that scenario. Otherwise, we'll get in that infinite recursion depth exceeded scenario. So a good place to start is to consider numbers that are really small. So as a hint, always consider, whenever you think about recursion, it helps to think about small numbers if we're subtracting towards those small numbers. So we can say, maybe, for example, if n equals 0, what does that mean in terms of our program? If n is 0, I have no chocolate. I have no chocolate. If n is 0, I have no chocolate. How come I still have one combination? This is pretty tricky, so we'll talk about this some more. Otherwise, if n is less than 0, I have no combinations. This is really bizarre. I said if n is 0, if I have no chocolate, somehow I still have one valid combination. Doesn't really reason out. But we'll kind of see how that unfolds later. Otherwise, if my number of parts is 0, if I can only give up to 0 pieces, then I don't have a valid way of making combinations either. So I think these two cases are kind of intuitive. If I have a negative pieces of chocolate, then I obviously can't give any chocolate to anyone, right? And if my maximum number of pieces of chocolate I can give out, if that is 0, then I can't give out any chocolate to anyone because I said my limit is 0. But how come this has to be 1? What happens if I change that to 0? Any thoughts? Think back to the ib tree. What happens if I change that base case to 0? Do you want to shout it out a little bit more?
I think that is that means that you need chocolate.
That means I need 1 chocolate? Okay, yeah. I think I kind of see that. So we do need 1 chocolate. We need some way of forming a valid solution, I think. Because both of these cases, you could think of them as I'm covering the invalid solutions. This is really important. Both of these cases cover the invalid solutions, where I return 0 because I say I have no way of making this combination. But if I were to make this a failure case as well, if I made this case return 0, what I would get is all of these cases would return 0. And if we think back to the fib tree, let's flip back to the fib tree. Fibonacci. Think back to the fib tree. Look at all this stuff. It is a mess. But the thing we want to notice here is that what we did with fib was we added up the base cases. 0 plus 1. Should be 0 plus 1. 0 plus 1. So we added up all those base cases to produce some kind of result. But if all of our base cases return 0, we'll be doing 0 plus 0 plus 0 plus 0 plus 0 plus 0 plus 0. And so our total number of combinations will be 0. So we need some kind of way to terminate in a successful case, in a valid combination. And so this requires some deep thinking about this problem. Oops, let's look ahead. This requires some deep thinking about this problem. Let's look at it this way. So let's say I'm trying to solve this problem. Find the number of ways you can count 2 pieces of chocolate, given that one, nobody can have more than 4 pieces. Right? Count partitions 2 of 4. What I'll do is I can try, for example, calling count partitions of, let's look at our code. If I start with count partitions 2, 4, I'm not at a base case, right? So I'll try this. 2 minus 4, that'll be -2. So I'll use the failure case. So with m, if I try to give someone 4 pieces, I say, no way, you can't have 4 pieces. I don't have that much chocolate. I could try that without m. Count partitions 2, 3. And when I make that recursive call, what I'll do is I'll say recursive case, 2 minus 3 is -1. That's not a valid combination again. But then I'll finally try count partitions 2, 2. This is the key point. When we try this count partitions 2, 2 recursive call, what we'll do is we'll say it's still not a base case, but when I hit this with m, I'll be calling count partitions 2 minus 2. We want this to be a correct case, right? We want this to be a correct solution. We know it is a correct solution. So we want it to be count partitions 0, 2. And I know if n is 0, if I make that a valid solution, then it'll report it as a valid solution. So the reason why we use this as a successful case is because we see that we need it here. We need it when I'm trying to figure out that count partitions 2, 2 case. Because I know if I say I have 2 pieces of chocolate and I want to hand out 2 pieces of chocolate, that is a valid solution. So because this base case, because our answer to that larger question relies on this base case, this is why this has to be valid. And that's all the time we have for today. Thank you so much.